In this video, we will discuss sidebands, basebands, and spectral windows, what they are, what limits they have, and how to optimally combine them in Alma to meet your science goals. Alma's highly customizable observing setup allows us to set our desired spectral resolution, observe spectral lines and continuum emission simultaneously, and choose our polarization products, among other things. Collectively, these observing parameters are called a spectral setup, or sometimes a tuning. While Alma is capable of many flexible tuning setups, there are some important constraints on what we can choose. These constraints come from the underlying architecture of Alma's receivers and correlator system, so it's important to understand how these systems work together.
In order to produce our final data, Alma combines the sky signal from its receivers, located at each antenna, with a series of local signals that we create. The first local signal creates what we call sidebands. The next creates basebands, and the final one creates spectral windows. This final step happens inside the correlator, which is also where the signal from all the individual antennas is combined.
Let's start by following the sky signal as it travels through Alma's receivers. When the sky signal reaches the detectors, we combine it with a locally generated signal of known frequency. This signal is created by a component called the local oscillator, or LO. The LO is what determines which range of frequencies we can observe within a given tuning. When we combine the LO signal with the sky signal, we end up with two specific windows in frequency space that we can observe. The windows we create are called sidebands, and we can't detect anything outside of those sidebands. One sideband will be slightly lower than the LO frequency, and one will be slightly higher. The sideband at lower frequencies is called the lower sideband, or LSB, and the one at higher frequencies is called the upper sideband, or USB. There will always be a gap between the LSB and the USB. We can shift which frequencies the sidebands cover by changing the frequency of the local oscillator.
It is important to note that although an LO creates two sidebands, sometimes we can only use one. Alma's Band 1 receiver, for example, only uses the upper sideband. Also, sometimes the upper and lower sidebands are both available, but are superimposed on each other and only separated later on. This is the case for the Band 9 and 10 receivers. It is important to be aware of these special cases when planning your observing setup. Once we have our sidebands, we combine them with the signal from the second set of local oscillators to create basebands. For Alma, basebands are frequency windows about 2 GHz wide within our sidebands, and they are an intermediate step in our signal processing procedure. Alma uses 4 LOs to create basebands, so we can create up to 4 basebands per observation, located anywhere within the sidebands. Currently, Alma allows you to place between 0 and 4 basebands within a given sideband. However, if you are using both sidebands, you cannot place 3 basebands in one sideband and the last baseband in the other. Much like the sideband frequencies, this limitation exists because of the way basebands are created.
Finally, we combine the signal of each baseband with another set of local oscillators to create spectral windows. Spectral windows are the regions of frequency space over which we actually record the spectra. You can place up to 4 spectral windows in a single baseband, which means you can have up to 16 spectral windows per tuning. Spectral windows can overlap with each other, and so can basebands. However, each spectral window has to fit completely within a baseband, and spectral windows and basebands both have to fit completely within a sideband. Let's look more closely at spectral windows. With Alma, you can fine-tune the center frequency, bandwidth, and frequency resolution of each spectral window separately.
Let's say that you're observing a target whose true spectrum looks like this. When we observe this target with our chosen spectral window, the spectrum will be sampled with a certain frequency resolution. Each frequency bin within the spectral window is called a channel, and all channels in the same spectral window will have the same frequency width. Channel width and bandwidth are closely linked. For example, if we select a channel width of 1 MHz and we have 10 channels, our spectrum might look like this. Note that because we have 10 channels of width 1 MHz each, our total bandwidth for this spectral window is 10 MHz. If we choose a finer channel width for our observations, say 0.2 MHz, we will get better frequency sampling, but the total bandwidth across our 10 channels will decrease to 2 MHz.
Remember from the radiometer equation that the sensitivity depends inversely on the square root of the channel width. Decreasing the channel width will increase the noise. If you need both a small channel width and high sensitivity, you will need to observe for longer in order to achieve your desired signal-to-noise. As we mentioned earlier, you can place up to 4 spectral windows in each baseband, and you can mostly customize each spectral window independently of the others. However, each spectral window has to have the same native channel width. This is because the correlator creates thousands of channels for each baseband, and then those channels are divided up amongst your spectral windows. Most standard observing setups will allow for about 2,000 channels, but you can create up to 8,000 channels for some setups. You can choose to assign all 2,000 channels to a single spectral window, in which case you will have one spectral window in that baseband. Or you can create 2 spectral windows with 1,000 channels each, 1 window with 1,000 channels and 2 with 500 channels, or 4 spectral windows with 500 channels each. This last option is especially useful if you have multiple lines in one baseband that you want to study in detail. Your spectral resolution is also related to your channel width. When you create your spectral windows, you will choose from a list of available channel widths. Then, by default, Alma averages channels together to give you your final spectral resolution. The default averaging is 2 channels, but you can select averaging of 1, 4, 8, or 16 channels instead if you need finer or coarser spectral resolution. Note that you cannot get better resolution than the width of a single channel. Finally, the more channels we have, the greater our total data volume is. Some Alma tunings use tens of thousands of channels, and the data volume in those observations can be very high. High data volumes mean the data take longer to process through the pipeline, to load into image viewers, and to be used in numerical calculations. All spectral window setups are therefore a balance of bandwidth, spectral resolution, sensitivity, and data volume.
We have just taken a brief look at sidebands, basebands, and spectral windows for Alma. Alma's receiver flexibility is one of its most powerful and useful features, allowing Alma users to create highly customized spectral setups for their science goals. Consider checking out some of our other videos linked on the screen now. Happy observing!